Our universe is held together by an invisible skeleton. This hidden framework, known as the cosmic dark matter web, dictates the placement of every galaxy while remaining completely undetectable to our eyes and instruments. By the end of this journey, you will understand the 25 deepest mysteries surrounding this cosmic architecture. We will confront how something we cannot see could be the most important structure in existence, and why its true nature has escaped the world's brightest minds for decades. What single cosmic question do you find most compelling? This invisible architecture is the first and most profound mystery. We call it the cosmic dark matter web, but what is it truly? Think of the entire universe as a single, unimaginably vast structure. The glittering galaxies we see through our telescopes are merely the sparkling lights on its surface. The dark matter web is the underlying framework, the beams and girders holding everything together. It is a network of filaments, immense threads of an unknown substance stretching across billions of light years. These filaments connect at dense nodes where thousands of galaxies swarm together in massive clusters. Yet, for all its undeniable influence, this entire framework is completely invisible. It does not emit, reflect, or absorb light of any kind. It is utterly dark. So how can we possibly know it is there? The answer lies in gravity. Astronomers watch the way galaxies move and rotate. They observe how light bends as it travels through seemingly empty space. These motions and distortions are far too powerful to be explained by the gravity of the visible stars and gas alone. There must be an immense amount of extra mass, a hidden source of gravity sculpting the cosmos. This is the ghost in the cosmic machine, its presence revealed only by the pull it exerts on everything we can see. We are left to map a shadow, tracing the outline of a structure we will never directly witness. What kind of substance can form such a perfect, all-encompassing web while remaining forever hidden from our most powerful instruments? This ghostly presence leaves us with a monumental challenge. How do you map something that cannot be seen? This is the second great mystery, the struggle of mapping the unmappable. Our only tools are the subtle ripples this dark web creates in the fabric of reality itself. The most powerful of these tools is a phenomenon known as gravitational lensing. Imagine space as a vast, taut sheet of rubber. If you place a heavy object on it, the sheet will warp and bend. Now, picture a beam of light traveling across this warped surface. Its path is no longer a straight line, it follows the curve. This is precisely what happens on a cosmic scale. The immense gravity of a dark matter filament, though invisible, acts like that heavy object warping the space around it. When light from a galaxy billions of light years away travels toward us and passes through one of these filaments, its path is bent. From our viewpoint, that distant galaxy does not look like itself. Its image is stretched and twisted into faint, ethereal arcs, like a reflection in a funhouse mirror. These cosmic mirages are our only clues. Astronomers painstakingly analyze these distorted images, measuring how much the light has been bent. By reverse engineering this distortion, they can calculate the mass that must be causing it. It is a process of celestial cartography, drawing the outlines of an invisible continent by studying how it distorts the horizon behind it. Every strange arc of light is a data point, a single stroke in a map of shadows. The resulting charts reveal a universe webbed with these dark matter rivers, a hidden geography that has dictated the flow of cosmic evolution since the beginning of time. But what if our maps are incomplete or worse, fundamentally misunderstood? Yet even with these ghostly maps in hand, we confront a puzzle of cosmic proportions. How did this intricate web of dark matter filaments first come to be? Its origin story is the third great mystery, one that takes us back to the very first moments of our universe. The leading theory suggests this entire cosmic architecture was born from the tiniest of seeds, quantum fluctuations in the primordial void. In the unimaginably hot, dense state immediately following the Big Bang, the universe was a seething cauldron of energy. At the quantum level, empty space was not truly empty. It was a turbulent sea where pairs of particles and their antiparticles would spontaneously blink into and out of existence. These fleeting, microscopic ripples in the fabric of reality are the key. For a fraction of a second, the infant universe underwent a period of hyper-accelerated expansion known as inflation. It ballooned in size at a rate far faster than the speed of light. During this incredible growth spurt, those infinitesimal quantum ripples were stretched. They were magnified from the subatomic scale to a scale spanning the entire cosmos. The denser spots in this stretched quantum tapestry, regions with just a tiny bit more energy, became the blueprints for the future. After inflation ended, gravity got to work. Over billions of years, it relentlessly pulled matter toward those original, amplified ripples. The slightly denser regions attracted more and more dark matter, slowly sculpting the vast, interconnected network of filaments we detect today. So the grand cosmic web, with its threads stretching across billions of light years, began as a whisper in the quantum static of creation. It is a humbling thought that the largest structures we can conceive were imprinted by the very smallest phenomena physics allows. But this elegant theory raises a new and troubling question. If the dark matter web was born from these quantum seeds, what exactly was it that got stretched? What is the true nature of the substance that forms the universe's hidden skeleton? This brings us to the heart of the enigma, the fourth and perhaps most frustrating mystery. What is this invisible stuff actually made of? For decades, physicists have proposed a menagerie of hypothetical particles, each one a potential candidate for the universe's hidden architect. The leading contender for a long time has been a class of particles known as WIMP, which stands for weakly interacting massive particles. As their name suggests, these would be heavy particles that rarely interact with normal matter, communicating with our world only through gravity and the weak nuclear force. This aloof nature would perfectly explain why dark matter effortlessly passes through our planet and us without a trace. Another compelling candidate is the action, a particle conceived to solve a different deep puzzle in particle physics. Actions would be incredibly light, potentially trillions of times lighter than an electron, and would swarm through space in unimaginable numbers. The hunt for these phantoms has been one of the most ambitious scientific endeavors of our time. Deep underground, in abandoned mines and beneath mountains, scientists have built exquisitely sensitive detectors. These labs are shielded from cosmic rays, their cores cooled to temperatures near absolute zero, all in the hope of catching a single telltale sign. They wait for the minuscule flash of light or the tiny amount of heat that would be produced if a dark matter particle, after its cosmic journey, finally bumped into an atom of normal matter. Yet, after decades of searching with increasingly sensitive instruments, the result has been the same: nothing. The detectors remain silent. We are left with a profound contradiction. The evidence for dark matter's gravitational influence is overwhelming, a cosmic certainty. Yet, the substance itself remains utterly elusive, refusing to reveal its identity in any lab on Earth. This failure to make direct contact is, in itself, a monumental clue. It tells us that dark matter is even stranger and more removed from our reality than we ever imagined. Could our leading theories be completely wrong? Are we searching for the right thing in the wrong way, or is the universe's hidden skeleton built from something beyond our current physics? This silent hunt for a phantom particle leads us directly to the web's ultimate purpose. Why does this invisible architecture even matter? Its true cosmic role is the fifth great mystery, one that reveals it as the master architect of the visible universe. The dark matter web did not simply form and then sit idly by. It became the universe's construction scaffold, the essential blueprint without which galaxies like our own Milky Way could never have been built. Picture the web's dense intersections, the nodes where multiple dark matter filaments cross. These regions act as immense gravitational wells, cosmic sinkholes pulling in everything nearby. Vast clouds of primordial hydrogen gas, the raw material for stars, were funneled along these invisible highways. Drawn by the irresistible pull of the unseen dark matter, this gas flowed into the nodes, piling up into ever denser masses. It was within these concentrated pools of gas, cradled by dark matter's gravity, that the first proto-galaxies ignited. Think of the dark matter web as a colossal irrigation system for the cosmos. Its filaments channel the flow of gas, directing it to specific fertile zones where galaxy formation can begin. Without this guiding framework, the gas would have remained a diffuse, thin haze, never gathering enough to collapse and spark into stellar fire. The galaxies we see today, from majestic spirals to blazing ellipticals, are not scattered randomly across the void. They trace the hidden architecture, glowing like cities built at the intersections of a global highway system we cannot see. This raises a profound question about our own cosmic home. Is the Milky Way's specific size, shape, and position a direct result of the dark matter node it formed within? The invisible web does not just tell galaxies where to form, it dictates how they evolve, how they spin, and even how they will eventually die. We are living testaments to the power of this hidden framework, our entire galactic neighborhood shaped by a force we are still struggling to comprehend. But this elegant cosmic blueprint is not without its flaws. A glaring inconsistency has emerged between our theoretical maps and the actual sky, a conflict known as the missing satellite problem. Our most sophisticated computer simulations of the universe, based on everything we think we know about dark matter, paint a very specific picture of our galactic neighborhood. They show that a large galaxy like our Milky Way should be surrounded by a vast swarm of thousands of smaller dark matter clumps. Each of these dense knots of invisible matter should have acted as a gravitational seed, pulling in enough gas to form a small, faint dwarf galaxy. According to the math, our sky should be filled with these tiny, orbiting satellite galaxies. Yet when we look, we find only a few dozen. The thousands predicted by the simulations are simply not there. It is as if we have the blueprint for a bustling metropolis, but when we arrive, we find only a handful of scattered villages. This is not a small accounting error, it is a fundamental mismatch. The universe appears to be far emptier on small scales than our best theories insist it should be. So where did all the missing satellites go? One possibility is that they did form, but most were too faint to survive. Perhaps the intense tidal forces from the Milky Way's gravity ripped them apart before their stars could truly shine. Another, more intriguing idea is that our understanding of dark matter itself is flawed on these small scales. Maybe dark matter particles interact with each other in ways we have not anticipated, preventing the smallest clumps from ever coalescing. This missing satellite problem is a ghostly census with profound implications, forcing us to question whether the invisible web is woven as finely as we believe. This ghostly census reveals an even deeper contradiction, a problem so perplexing it has been named the too big to fail mystery. While we struggle to find enough small satellite galaxies, the ones we do observe present a puzzle of their own. Our most powerful computer simulations of cosmic evolution suggest a clear rule. The most massive clumps of dark matter, the ones that form the largest dwarf galaxies, should also possess the most powerful gravitational pulls. This strong gravity should act as a protective shield, allowing these large dwarfs to hold onto vast amounts of their gas and form huge numbers of bright new stars. They are, in theory, too massive and gravitationally robust to fail at forming thriving stellar populations. Yet when we look at the actual dwarf galaxies orbiting our Milky Way and our neighbor Andromeda, we find a strange population of giants that look like ghosts. These dwarfs are large in physical size, stretching across thousands of light years, but they are eerily dim. They contain very few stars, and their old red stars suggest their star formation died out long ago. According to the simulations, galaxies of this sheer size should be blazing with stellar light, but they are not. They are cosmic underachievers, massive yet faint. This forces a difficult question. How can a galaxy be so large and yet so dark? One possibility is that these dwarfs do have massive dark matter halos, but something prevented them from ever turning their gas into stars. Perhaps an early burst of supernova explosions blew away their gas supply, or maybe the intense radiation from the first galaxies sterilized them. Another, more radical idea is that our understanding of dark matter's behavior is incorrect. Maybe dark matter particles are not completely cold and collisionless. What if they can interact with themselves, generating a form of friction that smooths out the cores of these halos, making their gravity too weak to hold onto star-forming gas? The too big to fail problem is not just a minor inconsistency. It strikes at the core of our models, suggesting that the dark matter web might not sculpt galaxies in the simple, predictable way we have long assumed. If the universe's fundamental construction material behaves in ways we have not anticipated, what other cosmic surprises are waiting to be uncovered? This disagreement over the cores of galaxies cuts to the very heart of our cosmic models. The eighth mystery is a fierce debate known as the cuspy halo problem, a conflict between what our simulations predict and what our telescopes see at the centers of the smallest, darkest galaxies. According to the standard model of dark matter, which assumes it is cold and collisionless, the gravitational pull at the very center of a dark matter halo should be incredibly intense. The density of this invisible matter should spike sharply toward the core, creating what physicists call a cusp. Imagine a mountain with an impossibly steep, sheer cliff face at its very peak, a dramatic and sudden rise in gravitational strength. This is what our most trusted simulations consistently show. Yet, when astronomers study the motions of stars within dwarf galaxies, they find something entirely different. The stars orbit the galactic center as if they are rolling across a gentle, rounded hill. The data suggests the dark matter density is constant in the inner region, a placid core instead of a sharp cusp. It is as if we predicted a needle's point and found a smoothed-over plateau. This is not a minor discrepancy. It implies that something is actively preventing dark matter from piling up at the centers of these galaxies, a process our models do not account for. One possibility is that we are wrong about dark matter itself. Perhaps its particles can interact with each other, creating a form of internal pressure that pushes back against gravity's pull and flattens out the central density. Another, equally fascinating idea points to the violent power of normal matter. Could the furious cycles of star birth and death have reshaped the dark matter core? When massive stars are born, they live fast and die young, exploding as supernova. These colossal explosions can blast the surrounding gas out of the center of a small galaxy. As this gas is violently ejected, the gravitational landscape of the galaxy changes abruptly. Without the constant pull of the gas, the dark matter particles might slosh back and forth, their collective motion effectively eroding the sharp cusp into a smooth core through a kind of gravitational friction. So the question becomes a cosmic chicken and egg puzzle. Is the core we observe a fundamental property of the dark matter particle, a signature of its intrinsic nature, or is it a secondary effect, a scar left by the dramatic astrophysical tantrums of the very first stars? The cores versus cusps controversy forces us to ask whether we are seeing the true face of dark matter, or merely the aftermath of a billion-year stellar war that reshaped its home. These cosmic disagreements over gravity's grip on small scales are mirrored by a growing conflict on the grandest stage of all. The ninth mystery, known as the Hubble tension, pits the entire observable universe against our fundamental models. At its heart is a deceptively simple question. How fast is the cosmos expanding? For a century, we have known that galaxies are rushing away from each other, their light stretched to redder wavelengths by this relentless cosmic flight. The rate of this expansion is called the Hubble constant, a single number that should be one of the most certain facts in all of cosmology. Yet modern measurements have created a crisis. Two powerful, independent methods now give two different, stubbornly incompatible answers. The first method looks at the very early universe. It uses the pristine afterglow of the Big Bang, the cosmic microwave background, as a cosmic baby picture. By analyzing the subtle patterns in this ancient light, we can extrapolate forward through 13.8 billion years of cosmic evolution to predict what the expansion rate should be today. This method provides a very precise but indirect measurement. The second method looks at the local, modern universe. Astronomers observe pulsating stars known as Cepheid variables and cataclysmic stellar explosions called Type Ia supernova in relatively nearby galaxies. These objects are standard candles, meaning we know their true brightness. By measuring how dim they appear from Earth, we can directly calculate their distance and thus directly measure the current expansion rate. Both methods are exquisitely refined, and both are performed by teams of brilliant scientists, but they do not agree. The local universe appears to be expanding significantly faster than the early universe's blueprint says it should be. This is not a small margin of error. It is a persistent and significant gap that has survived over a decade of increasingly precise observations. So where does the dark matter web fit into this? The invisible cosmic skeleton is not a passive bystander in the universe's expansion. Its gravitational pull acts as a cosmic brake, a counterforce working against the momentum of the Big Bang. The precise density and distribution of the dark matter web is a critical input in the equations that predict how the expansion rate should have evolved over time. If our maps and models of the dark matter web are subtly incorrect, if its gravitational influence is not quite what we think, then our predictions for the expansion rate will be wrong. Perhaps the web is more clumpy or more diffuse on very large scales than our simulations assume, altering its braking power. Or maybe dark matter itself possesses some strange, unknown property that causes it to interact with the expansion of space in a new way. The Hubble tension is more than a disagreement over a number. It is a direct challenge to our standard model of cosmology, a model that depends entirely on the dark matter web behaving as we expect. This conflict suggests that our understanding of the universe's hidden architecture and its role in the cosmic drama may be missing a crucial piece. While we map the universe's crowded intersections, its empty spaces hold an equally profound secret. The 10th mystery takes us into the great cosmic voids, the sprawling deserts within the dark matter web. These are not mere gaps between the filaments, they are immense, structured regions of near-nothingness. Some voids stretch for hundreds of millions of light-years, volumes of space so empty they could contain thousands of galaxies like our own, yet hold only a handful of isolated, lonely stars. How can such vast territories of the cosmos remain so desolate? The answer lies in the dark matter web's gravitational dynamics. The filaments and nodes act as cosmic attractors, their immense pull drawing matter inward. The voids, by contrast, are the repellers. They are regions of incredibly low density, where the gravitational pull is so weak that it cannot hold onto anything. Think of the universe as a landscape of hills and valleys, but governed by gravity. The galaxies and dark matter clusters are the high mountain peaks and ridges where matter naturally gathers. The voids are the deep, sinking valleys. Any speck of gas or dust that finds itself in a void experiences a collective gravitational push from the surrounding web, a force that actively sweeps it out toward the crowded filaments. It is a cosmic evacuation, a billion-year process that leaves these regions barren, but the voids are not completely empty. Their profound quiet makes them perfect laboratories. The sparse gas that remains is often slightly warmer than the gas in the filaments, heated by the faint shock waves of cosmic evolution. And the few galaxies that do form in these isolation chambers are often strange, misshapen objects, starved of the galactic interactions that drive evolution elsewhere. They are cosmic wallflowers, forever watching the vibrant dance of the clusters from a distance. This raises a startling possibility. Could the properties of these voids, their sheer size and emptiness, be a more sensitive test of dark matter than the crowded clusters themselves? In the silence of nothing, we might finally hear the whisper of the invisible web's true nature. This cosmic skeleton was not born fully formed. It has a life story, a history of growth and change spanning billions of years. How did the delicate quantum ripples of the infant universe transform into the vast, gnarled web we infer today? To uncover this evolution, we must turn to the most powerful time machines we possess, not telescopes but supercomputers. Scientists create entire universes inside these machines, starting with the smooth, hot soup of the Big Bang and seeding it with the same tiny fluctuations. They then set the laws of physics in motion and let the simulation run, watching as gravity works its magic over eons of virtual time. The results are breathtaking digital films that chart the web's entire life cycle. In the earliest epochs, the universe looks like a cosmic sponge, a froth of small, interconnected bubbles. Dark matter, drawn by its own gravity, begins to drain from the broad, empty regions into the faint, emerging filaments. You can watch these tendrils thicken and strengthen like roots growing through soil. Over time, the smaller filaments merge, feeding larger and larger structures. It is a slow-motion river system, with tiny streams combining into mighty rivers that all flow toward the ocean like galaxy clusters. This growth is not gentle. The simulations reveal a violent, dynamic process. Filaments whip and sway, sometimes stretching, sometimes snapping as dense nodes pull them in. Entire sections of the web can collapse, their material consumed by a growing cluster. The web is not a static sculpture, it is a living, breathing architecture, constantly being rewired by the relentless pull of gravity. But these simulations also pose a profound question. Has the fundamental nature of the web remained constant, or has its very texture and behavior changed over cosmic time? Some theories suggest that the web's connectivity, the way its strands link together, might have been different in the distant past. Perhaps the threads were finer, the nodes more numerous but less massive. By comparing these virtual histories with real observations of the most ancient light and the earliest galaxies, we are searching for the ghostly signature of the adolescent web. Finding a mismatch would be revolutionary, indicating that the invisible stuff itself or the rules it plays by are not the constants we believe them to be. The web's evolution is its own biography, and we are only now learning how to read its first chapters. This silent conflict between expansion and gravity leads us to a radical possibility. What if the two greatest cosmic unknowns are not strangers but are secretly entwined? The 12th mystery probes a tantalizing idea that dark matter and dark energy might interact. For decades, cosmology has treated them as separate entities. Dark matter pulls, its gravity working to build structure and slow the universe's expansion. Dark energy pushes, an enigmatic force causing that expansion to accelerate. They are the cosmic yin and yang, one sculpting the cosmos, the other tearing it apart. But what if this clean separation is an illusion? Some theorists propose that dark matter and dark energy could be two faces of a single, unified dark sector. In this view, they are not passive opponents but are engaged in a continuous exchange of energy. Imagine a cosmic battery where dark matter slowly leaks its energy into dark energy, or perhaps the reverse. This interaction would not be a dramatic collision, but a subtle, persistent transfer happening everywhere in space at once. Such a connection would fundamentally alter the life story of the cosmic web. If dark matter is slowly converting into dark energy, its gravitational grip would be weakening over cosmic time. the web's filaments might be thinning, their ability to pull in new material fading as the universe ages. This could leave a distinct imprint on the large-scale structure we observe today, perhaps explaining why the web appears slightly more diffuse on the larger scales than our standard models predict. More profoundly, this interaction could be the key to resolving the Hubble tension. The disagreement over the universe's expansion rate hinges on how the tug-of-war between dark matter's pull and dark energy's push has evolved. If they are interacting, then the strength of this push and pull is not constant. The breaking power of dark matter could have faded differently than we assumed, or the acceleration from dark energy could have kicked in at a different time. A subtle, ongoing conversation between the two could perfectly account for why the local universe is expanding faster than our non-interacting models forecast. We are left with a breathtaking question. Are we witnessing not just a hidden structure but a hidden relationship? The cosmic dark matter web may not be a static skeleton, but a living entity in a delicate dance with the very force that seeks to dissolve it. Deep within the cosmic voids and threaded along the invisible filaments, another hidden force weaves through the darkness. The universe is laced with magnetic fields, imperceptible lines of force that stretch between galaxies and across the great voids. Their origin is one of astronomy's oldest puzzles, and now we must ask if they are entangled with the dark matter web itself. How could an invisible structure influence something as fundamental as magnetism? The process begins with the faintest seeds. In the early universe, turbulent motions of primordial plasma could have generated minuscule magnetic fields. These initial fields were incredibly weak, far too feeble to shape the cosmos. But as structure formed, the dark matter web provided a colossal amplifier. Picture a vast, invisible filament, a river of dark matter pulling immense flows of ionized gas along its length. This gas is not flowing smoothly, it is a chaotic, turbulent river. As these charged particles swirl and collide within the confines of the filament, they stretch and twist the weak magnetic field lines. This dynamo effect, similar to how the Earth's molten core generates our planet's magnetic field, can amplify those feeble seeds into powerful, large-scale fields. The web acts as a cosmic loom, using the flow of gas guided by its gravity to weave magnetic energy into the fabric of space itself. But this leads to a deeper, more speculative question. Could dark matter itself be the source? We have always assumed dark matter is completely neutral, oblivious to electromagnetic forces. What if a small fraction of it possesses a tiny magnetic moment, a faint ability to interact with these fields? Or what if the gravitational influence of the web is so precise that it directly triggers the instabilities which generate magnetism in the first place? The magnetic fields we detect today, which guide cosmic rays and influence star formation, might be the direct offspring of the dark matter architecture, a visible signature of the invisible web's dynamic power. This forces us to wonder if we are seeing two separate mysteries, or a single, unified hidden force shaping our universe in ways we are only beginning to trace. Our inventory of the cosmos reveals a startling shortfall. When we tally all the normal matter in the universe, the protons and neutrons that make up stars, planets, and our own bodies, we find that more than half of it is simply missing. This is the 14th mystery, the case of the lost baryons. We know this matter must exist because our measurements of the early universe from the cosmic microwave background give us a precise ledger of the total amount of ordinary matter created in the Big Bang. But when we look around at the modern universe, counting every galaxy, star, and cloud of cold gas, we come up dramatically short. It is a cosmic accounting error on a colossal scale. So where did it all go? The leading theory points directly to the dark matter web. Astronomers suspect this missing normal matter has been heated to millions of degrees and blown into a vast, ultra-diffuse fog that fills the spaces between galaxies. This searing hot gas is concentrated in the very filaments of the cosmic web, trapped there by the immense gravitational pull of the invisible dark matter. Think of it as a ghostly atmosphere for the universe's hidden skeleton, an ocean of plasma so hot it glows not in visible light but in low-energy X-rays. Detecting this faint, diffuse glow is one of the greatest observational challenges in modern astronomy. It is like trying to see the warm breath of a person on a cold day from miles away. Our best hope lies in a clever trick of nature. When the light from brilliant, distant objects called quasars travels through these filaments on its way to Earth, the hot gas absorbs specific wavelengths. This leaves minuscule dips in the quasar's spectrum, like unique chemical fingerprints imprinted on the light after its billion-year journey. By finding these fingerprints, we can confirm the presence and composition of the missing matter. Another method is to look for the faintest possible X-ray glow emanating from the web itself, a task requiring incredibly sensitive space telescopes. Solving this mystery is crucial because it completes the picture of our cosmic habitat. The dark matter web provides the scaffolding, and this hot, hidden gas is the final piece of the normal matter puzzle, the majority of the tangible stuff from which everything we see is built. Finding it would mean we finally understand the full inventory of our universe, closing a gap that has haunted cosmology for decades. But its elusiveness forces us to ask a deeper question. Is this gas truly missing, or have we simply been looking for it in the wrong way, with instruments that cannot yet perceive the universe's most dominant form of ordinary matter? These ghostly filaments may even guide the most energetic travelers in the universe. As we push past the missing matter, we encounter the 15th mystery, the web's subtle influence on cosmic rays. These are not rays of light, but atomic nuclei stripped of their electrons, hurtling through the void at nearly the speed of light. Each one carries a phenomenal amount of energy, a subatomic bullet fired from an unknown cosmic cannon. Their origins have puzzled scientists for over a century, and the paths they take to reach us are long and winding. This is where the invisible web may leave its mark. Space is not a perfect vacuum. It is filled with a tangled web of magnetic fields, the very fields the dark matter filaments help to amplify. A cosmic ray, being a charged particle, does not travel in a straight line. It is deflected and spun by these magnetic fields, its path becoming a chaotic pinball journey across millions of light years. By the time one reaches our detectors, its original direction is completely scrambled, hiding the location of its source. But the dark matter web's role may be more direct. Its immense gravitational fields, stretching across the vast cosmic voids and dense clusters, can act as subtle lenses for these particles. Just as gravity bends the path of light, it can also bend the path of matter, even matter moving at relativistic speeds. Could the web's gravitational hills and valleys be focusing certain cosmic rays, creating unexpected hotspots of high-energy particles in our sky? Some puzzling observations suggest this might be the case. We detect a strange overabundance of cosmic rays arriving from specific regions of space that do not seem to contain any obvious powerful sources like active galaxies or supernova remnants. Perhaps these are not the sources at all, but rather focal points, places where the invisible gravity of the dark matter web has acted like a colossal lens, concentrating the paths of these particles from many different origins into a single, misleading bright spot on our cosmic maps. The web may not only build the cosmic architecture, but also orchestrate the journey of its most frenetic particles, leaving us to decode a celestial illusion. Perhaps the entire hunt for an invisible substance is a spectacular misdirection. The 16th mystery dares to ask the most radical question of all. What if the dark matter web is not there? What if we are not mapping a hidden structure, but are instead witnessing the slow failure of our most trusted law of physics? This is the core argument of alternative theories, most notably one called modified Newtonian dynamics, or MND. Its proposal is deceptively simple. Instead of inventing a new, invisible form of matter to explain why galaxies spin too fast, perhaps we should modify our understanding of gravity itself, specifically Newton's laws, in the realm of extremely weak forces. In the faint gravitational fields at the outer edges of galaxies, where the pull of stars becomes almost negligible, Mann suggests that gravity does not fade away as quickly as our standard equations predict. It gets a subtle, unexpected boost. This tiny modification, its proponents argue, is enough to explain why stars on the galactic fringe orbit at such high speeds without needing any dark matter at all. For certain individual galaxies, Mann works remarkably well. It can match the observed rotation curves with surprising accuracy, a success that its champions point to as proof that we are overcomplicating the cosmos. Why invent a universe filled with phantom matter when a simple tweak to gravity might suffice? Yet for most physicists, the evidence for an invisible cosmic web remains too overwhelming to discard. While Mann can sometimes explain the behavior of single galaxies in isolation, it struggles catastrophically with the big picture. It cannot easily account for the bullet cluster, a cosmic collision where the gravitational lensing effect is clearly separated from the visible matter, suggesting a massive, invisible something has passed right through. It has immense difficulty explaining the intricate patterns in the cosmic microwave background, the universe's baby picture, which requires dark matter's gravitational pull to form the observed ripples. And it cannot naturally build the vast, filamentary cosmic web that our telescopes have mapped through its gravitational effects. The dark matter hypothesis, for all its frustrations, provides a single, unifying architect for 1,000 different cosmic phenomena. Mann, by contrast, often requires ad hoc fixes for each new observation, like a mechanic constantly inventing new tools for every single broken car. The choice is stark. Do we live in a universe governed by familiar gravity but filled with a mysterious, invisible substance that shapes everything? Or is our universe made only of the matter we see, but governed by a stranger, modified form of gravity that we do not yet fully understand? Both options lead us into the unknown. The silence in our underground detectors may be telling us that dark matter is more exotic than we dreamed, or it could be a whisper that gravity itself holds secrets we are only beginning to hear. Deep within the heart of almost every galaxy, a supermassive black hole lies in wait. This 17th mystery asks if these cosmic monsters are nurtured by the invisible web itself. The dark matter filaments that channel gas into galaxies may also be the ultimate feeding tubes for the beasts at their centers. As vast rivers of gas flow along these gravitational highways, a portion could be directed straight into the galactic core, providing a constant, rich diet for the waiting black hole. This process might explain a profound cosmic correlation. Galaxies that reside in the densest nodes of the web, where the inflow of material is greatest, often host the most massive and active black holes. It is as if the web's architecture not only builds the city but also determines the size and appetite of its central power plant. But the connection might be even more intimate and strange. Could dark matter itself be fueling these engines? Some theories suggest that in the intense gravitational field surrounding a supermassive black hole, dark matter particles could be drawn into such dense concentrations that they begin to annihilate each other upon contact. This annihilation would be a process of pure energy conversion, releasing a torrent of radiation and heat. This could provide a powerful, hidden energy source that sustains the black hole's ferocious activity, especially in the early universe when other fuel was scarce. We are left to wonder if we are seeing two separate phenomena or a single, symbiotic system. Does the dark matter web simply deliver the food, or does it also act as the ghostly kindling that helps ignite the most luminous objects in the cosmos? The brilliant quasars that outshine entire galaxies may be the combined product of visible gas and the invisible web's most secret energy. This grand cosmic architecture faces a future of unimaginable tension. The 18th mystery forces us to contemplate the ultimate destiny of the dark matter web itself, a fate dictated by its silent war with dark energy. For billions of years, the web's gravitational pull has been the dominant force, tirelessly building structure and gathering matter into its intricate filaments and nodes. But this era of construction is ending. We now live in a universe where dark energy, the mysterious force driving accelerated expansion, has taken the reins. This sets the stage for a cosmic battle that will play out over trillions of years. The critical question is whether the web's gravity is strong enough to hold its structure together against the relentless pull of expanding space. The answer depends on scale. On the local level, within bound structures like our own local group of galaxies, gravity has already won. The Milky Way and Andromeda are destined to collide and merge, their fates sealed by the dark matter halos that bind them. Similarly, the great galaxy clusters, the densest nodes of the web, are likely to remain as isolated gravitational islands. Their dark matter scaffolding is simply too strong for dark energy to rip apart. But the vast filaments themselves, the long, delicate threads that connect these dense clusters, face a far more fragile future. As the universe accelerates its expansion, the space between these filaments will stretch at an ever-increasing rate. The gaseous highways that currently flow along them will be severed. New material will cease to arrive, starving future generations of stars. Over eons, these connecting strands will thin out, becoming tenuous bridges between increasingly isolated archipelagos of galaxies. In the most extreme scenario, if dark energy's strength increases over time, even the filaments themselves could be stretched and diluted beyond recognition. The cosmic web, the universe's defining structure, could slowly unravel, its connectivity lost forever. This leads to a haunting vision of the far future, a time when the universe is a collection of isolated galaxy clusters drifting apart in an ever-cooling, ever-darkening void, their shared skeletal framework dissolved by the relentless expansion of nothingness. The web's fate is not written in stone, but in the unknown nature of the very forces that govern reality. Will the universe's hidden skeleton endure, or is it destined to be the first casualty in dark energy's final victory? The universe's hidden architecture may be more than a gravitational blueprint. This 19th mystery asks if the dark matter web is a vast information storage system, its intricate pattern a frozen record of the cosmos's deepest operating code. Every twist in its filaments, every intersection of its nodes, could be a physical manifestation of the universe's fundamental laws, a cosmic hard drive written in the language of gravity. The sheer complexity of the web is not random. It emerged from the simple, elegant rules of physics acting upon those initial quantum seeds. But the specific pattern we see today, the exact arrangement of its billion light-year strands, might encode details about those rules that we cannot access any other way. Think of the web as a universal fingerprint. Just as the unique walls on a fingertip can identify a person, the specific geometry of the cosmic web could reveal the identity of the underlying physics that birthed it. Its structure is a direct output of the properties of dark matter itself. Is dark matter perfectly cold and collisionless, or does it have a tiny bit of internal pressure? Does it interact with itself in subtle ways? The answers to these questions would leave distinct imprints on the web's texture, changing the thickness of its filaments or the spacing of its nodes. By comparing our most detailed maps of the real web against billions of computer simulations, each using slightly different rules for dark matter, we are essentially running a cosmic decryption program. We are searching for the simulation whose virtual web perfectly matches the ghostly one we observe, and that match would tell us the true nature of the invisible particle. But the information content could run even deeper. Some theorists speculate the web might hold clues to physics beyond the standard model, perhaps even touching on the nature of space-time. The web is not painted onto space, it is space, or at least its gravitational curvature. Its structure is a direct map of how space-time itself has been warped and folded by the presence of this mysterious mass. Could the Webb's connectivity reveal something about the quantum structure of space-time at the smallest scales? Is the universe's largest structure a magnified projection of its tiniest, most fundamental building blocks? We are left with a staggering possibility. The cosmos may have written its own theory of everything, not in equations, but in the silent, invisible architecture that binds it together. The ultimate secrets of reality might not be found in a particle collider, but etched into the ghostly contours of the dark matter web, waiting for us to learn how to read them. Our very existence might be a direct gift from the dark matter web. This 20th mystery asks a deeply personal question. Was the specific architecture of our local cosmic filament necessary for life to emerge in the Milky Way? The answer appears to be a tentative yes. The web did not just dictate where our galaxy would form, it carefully managed the conditions for its development over billions of years. Consider the flow of gas that built our home. The gentle, sustained delivery of material along our local filament allowed the Milky Way to grow at a stable, regulated pace. This prevented the chaotic, explosive bursts of star formation that would have bathed our future solar system in lethal radiation. It also avoided the opposite extreme, a starvation diet that would have left our galaxy with too few heavy elements to ever form rocky planets like Earth. Our position within the web's architecture also provided a peaceful suburban environment, far from the violent cores of massive galaxy clusters where titanic collisions and intense radiation would have constantly sterilized any fledgling worlds. This cosmic nurture extends to the very elements that compose us. The long, quiet periods between galactic mergers, orchestrated by the web's large-scale dynamics, gave previous generations of stars the time to live, die, and seed the galaxy with the carbon, oxygen, and iron essential for life and planets. So we are not just residents of a galaxy, we are products of a specific, carefully crafted niche within the universe's grand, invisible infrastructure. This leads to a staggering anthropic thought. Could other cosmic webs be fundamentally different? In a hypothetical multiverse, perhaps other universes possess dark matter with slightly different properties. Some might form webs that are too coarse and sparse, failing to gather gas into stable galaxies. Others might be too efficient, rapidly funneling all matter into monstrous, short-lived superclusters where chaos reigns. In those alternate realities, the cosmic conditions for life might never arise. The silent, stable architecture we take for granted could be a rare and precious cosmic circumstance. We are left to wonder if the dark matter web is not just a physical structure, but a fundamental prerequisite for a living, thinking cosmos. Does our ability to ponder its mysteries depend entirely on its specific, life-friendly design? The quantum origins of the cosmic web take us back to a time before time, to a realm of pure potential. In the first fleeting moments after the Big Bang, the universe was a sea of seething energy where the very concepts of here and there or before and after had no firm meaning. This was the domain of quantum mechanics, where uncertainty is a fundamental law. Empty space was not empty at all, but a turbulent foam where particles and their antiparticles spontaneously flickered into existence for unimaginably brief instants before annihilating each other. This constant, frantic activity meant that the energy density of the universe could not be perfectly uniform. At the tiniest scales, there were inevitable fluctuations, tiny hills and valleys in the fabric of reality itself. These were the quantum seeds, the initial inhomogeneities born from the inherent uncertainty of the cosmos. For a fleeting moment, these ripples were microscopic, smaller than a single atom. Then inflation struck. The universe underwent a violent, hyper-accelerated expansion, ballooning from a subatomic speck to a volume larger than our entire observable universe in a fraction of a second. During this incredible growth spurt, those infinitesimal quantum ripples were stretched. They were magnified from the quantum scale to a cosmic scale, frozen into the fabric of spacetime as slight variations in density. Regions that had been a tiny bit denser due to a quantum fluctuation became vast, slightly denser patches in the primordial plasma. After inflation ended, gravity began its slow, patient work. It treated these stretched quantum fluctuations as a blueprint. Over billions of years, gravity pulled the dark matter and then the normal matter toward these slightly denser regions. The quantum whispers became gravitational shouts, amplifying into the vast network of filaments and voids we detect today. The grand cosmic web, with its threads stretching across billions of light years, is therefore a direct descendant of quantum uncertainty. Its entire structure is a ghostly monument to the random flickerings of the infant universe. This raises a profound and almost philosophical question. Is the specific arrangement of galaxies, the location of our own Milky Way, and by extension our very existence, ultimately a consequence of a random quantum roll of the dice in the first moment of time? That ghostly fingerprint of the cosmos holds a deeper secret in its geometry. The 22nd mystery asks why the dark matter web displays such striking large-scale symmetries and repeating patterns. When we step back to view the universe on its grandest scales, a certain order emerges from the apparent chaos. The distribution of galaxy clusters and the voids between them begins to look statistically similar, no matter which direction we gaze. This is not a perfect crystalline symmetry, but a more subtle, fractal-like repetition of forms. Voids of a certain size and shape appear again and again, and the angles at which filaments intersect seem to follow a hidden rulebook. Where does this underlying order come from? One compelling idea is that these patterns are a direct reflection of the universe's fundamental laws. The physics that govern the Big Bang were built upon profound symmetries, principles that remain unchanged regardless of where or when you are. The cosmic web, as the ultimate product of that initial state, might be imprinted with these primordial symmetries, its large-scale structure acting as a cosmic echo of the perfect order at the beginning of time. The patterns we see could be the universe's way of revealing its most basic, elegant operating code. Yet another possibility is that this order is not primordial but emergent. It could be the inevitable outcome of gravity's relentless work over billions of years. Think of it like a river system on Earth. No two rivers are identical, yet all share common features. They have tributaries, they meander, they form networks. This happens because water follows the path of least resistance, eroding the landscape according to universal principles of fluid dynamics and gravity. In a similar way, as dark matter and gas flowed through the evolving universe, gravity acted as the universal sculptor. The specific patterns we see, the characteristic sizes of voids and the thickness of filaments, may simply be the most stable, natural configurations that matter can settle into under gravity's inexorable pull. This is a classic cosmic puzzle. Are we seeing the fingerprint of fundamental physics, a direct projection of nature's deepest symmetries onto the sky? Or are we witnessing a complex, self-organizing system that creates its own order from the bottom up, much like a flock of birds forming intricate patterns without a leader? The answer likely lies in a combination of both. The initial conditions set the stage with their quantum symmetry, and gravity's play then directed the actors into the grand, repetitive patterns we observe today. Unlocking this mystery means learning to read the universe's architectural blueprint, discerning which lines were drawn at the dawn of time and which were sketched in by the slow, patient hand of gravity. This invisible scaffolding manifests most tangibly in the vast, spherical clouds we call dark matter halos. Each galaxy, from the smallest dwarf to the largest spiral, is embedded within one of these immense, unseen spheres of pure gravitational influence. They are the individual knots in the cosmic web, the local concentrations of power that dictate a galaxy's fate. Yet these halos are not simple, featureless blobs of darkness. They possess a rich and mysterious internal structure that challenges our understanding. The density of dark matter within a halo is not uniform. It increases dramatically toward the center, creating a powerful gravitational anchor point for the visible galaxy. This central density profile has become a focal point of intense debate, as we have seen with the cuspy halo problem, but the mysteries run even deeper. The very shape of these halos defies simple expectation. You might picture them as perfect spheres, but they are not. Computer simulations reveal that dark matter halos are triaxial, meaning they have 3 different axes like a cosmic potato. They can be stretched and flattened, their shapes molded by the gravitational tides of nearby filaments and the violent mergers with other halos throughout cosmic history. This subtle asymmetry is crucial, as it can influence how the embedded galaxy rotates and how new gas falls into fuel star formation. Perhaps the most mind-bending property is their substructure. A single, large dark matter halo is not a smooth entity. Simulations show it is more like a cosmic Russian nesting doll, containing within it the ghostly remnants of countless smaller halos that were swallowed during the galaxy's growth. These are the subhalos, dense clumps of dark matter that orbit within the larger halo-like moons around a planet. They are the invisible counterparts to the missing satellite galaxies, the dark matter scaffolding that never managed to attract enough gas to light up. This complex hierarchy of halos within halos reveals a violent, layered history of cosmic construction, a story of endless mergers and acquisitions written in invisible ink. The halo surrounding our own Milky Way should be teeming with thousands of these dark subhalos, each one a silent testament to a smaller galaxy consumed in the distant past. Their gravitational whispers may even be subtly perturbing the outer fringes of our galaxy, stirring the stellar halo in ways we are only beginning to detect. How does this intricate halo connect back to the grand web? The halo itself is fed by the larger architecture. Thin tendrils of dark matter, fine threads spun from the cosmic filaments, continue to funnel fresh material into the halo, a slow cosmic drizzle that sustains its growth over eons. The halo is not an isolated fortress, but a dynamic node in a living network, constantly exchanging influence with the vast invisible structure it calls home. We are left to wonder if every single galaxy, including our own, carries this complex, layered dark matter signature, a hidden history of violence and growth encoded in the invisible sphere that holds us all. The universe still echoes with the deep hum of its own creation. This resonant memory, known as the cosmic sound wave or Baryon acoustic oscillation, is our 24th mystery, and it provides a ghostly measuring tape for the invisible web. To understand this echo, we must travel back to the universe's first 400,000 years. At that time, the cosmos was not silent. It was a searing, dense plasma, a fluid of light and matter locked in a violent tug of war. Gravity, driven mostly by dark matter, was constantly trying to pull the plasma inward to form denser clumps. But the intense pressure of the trapped light, the photons, fiercely pushed back, creating a powerful outward force. This conflict set the entire universe ringing. Regions of plasma would collapse under gravity's pull, only to be blasted outward by the photon pressure, then pulled back in again. This created a spherical sound wave, a ripple of overdensity that expanded from every single one of those initial quantum seeds at nearly half the speed of light. This cosmic bell was ringing everywhere at once. Then, the universe cooled just enough for a pivotal change. Electrons and protons combined to form neutral atoms, a moment we call recombination. Suddenly, the photons were set free, creating the cosmic microwave background we observe today. The sound waves were instantly frozen in place, their progress halted. Each wave was left as a faint spherical shell of matter, a ripple with a very specific radius. This radius became a cosmic standard ruler, a single fixed distance imprinted on the fabric of space. For billions of years, gravity continued its work, with the dark matter web sculpting the distribution of galaxies. But that ancient ruler remained. When we create three-dimensional maps of millions of galaxies in the modern universe, we find a startling pattern. Galaxies are slightly more likely to be separated by a specific distance, the exact size of that frozen sound wave from the dawn of time. It is as if we dropped billions of pebbles into a pond simultaneously and then took a photograph billions of years later, still finding a faint, repeating pattern in the placement of lily pads. This is the Baryon acoustic oscillation, a ghostly echo of the universe's first sound, and it is here that the sound wave and the dark matter web meet. The precise way this standard ruler appears stretched or compressed in our maps tells us how the universe has expanded over billions of years. It allows us to measure the relentless push of dark energy and the gravitational pull of the dark matter web with incredible precision. The sound wave gives us a fixed scale to measure the very skeleton it helped to decorate. The oscillations confirm that the web's structure grew exactly from those initial seeds, and they provide one of our strongest independent checks on the amount of dark matter and dark energy in the cosmos. This silent echo from the beginning of everything has become one of our most trusted guides to the invisible architecture that now holds it all together. This final mystery brings us full circle back to the most fundamental and haunting question of all. What is the dark matter web truly made of? Our journey has revealed its gravitational might and cosmic influence, but its substance remains a ghost. The leading candidates have failed to appear in our detectors, forcing physicists to broaden the hunt to far more exotic possibilities. One idea revives an ancient specter: primordial black holes. These would not be the black holes formed from dead stars, but ones created in the unimaginable density of the Big Bang itself. They could range in size from a single atom to a massive planet, peppering the cosmos and weaving the web through their collective gravity. Yet, careful observations of stellar motions and the bending of light have largely ruled out black holes as the dominant form of dark matter, at least across most size ranges. Another fascinating candidate comes from the theoretical realm of supersymmetry, a concept that proposes every known particle has a heavier, unseen twin. The lightest of these supersymmetric particles, often called the neutralino, would be stable, massive, and barely interact with normal matter, making it a perfect WIMP candidate. For decades, this was the golden hope, but the Large Hadron Collider has yet to find any evidence for these particles, leaving supersymmetry in a precarious position. As these classic ideas are challenged, more radical proposals emerge. Could dark matter be composed of an entirely new class of ultralight particles, so wispy that they behave more like a pervasive wave than a discrete particle, their collective vibration forming the cosmic web? Or does it reside in a hidden sector, a shadow universe of particles and forces that parallel our own, interacting with us only through gravity? The future of this search is now branching out in creative new directions. Some experiments are looking for incredibly subtle signals, like the faint radio waves that might be emitted when actions, if they exist, convert into photons in the presence of strong magnetic fields. Others are designing ultra-precise atomic clocks and quantum sensors to detect the minuscule distortions that a passing wave of dark matter might imprint on the fundamental constants of nature. The next generation of telescopes, both on the ground and in space, will map the cosmic web in unprecedented detail, looking for any subtle flaw in its structure that betrays the true nature of its threads. The answer will not come easily. It may require us to fundamentally redefine what matter is, or to accept that most of the universe is built from something completely outside our current physical understanding. The silence from our detectors is not an end but a guide, pushing us toward a more profound and perhaps more beautiful truth. The cosmic dark matter web has shown us its power. The final step is to learn its name. 25 profound mysteries now stand before us, a testament to the vastness of our ignorance. From the ghostly presence of the web itself to the quantum seeds that birthed it, from its role as galactic architect to its silent war with dark energy, This invisible framework is the universe's most fundamental yet elusive feature. We have traced the missing satellites, questioned the too big to fail galaxies, and debated the cuspy cores of dark halos. We have seen how it might guide cosmic rays, store cosmic information, and even nurture the supermassive black holes that lurk in galactic hearts. This hidden skeleton dictates the placement of every galaxy, the flow of every intergalactic river of gas, and potentially the very possibility of our own existence. It is a structure we know primarily by its gravitational shadow, a cosmic certainty that remains a profound puzzle. The hunt for its true nature pushes the limits of our physics, from the silent caverns of underground detectors to the vast digital universes we simulate. Each unanswered question is not a failure, but a beacon guiding us toward a deeper understanding of reality. The dark matter web is the universe's greatest unsolved story, written in invisible ink across the cosmos. Which of its 25 mysteries captures your imagination the most? Share your thoughts in the comments below, and subscribe to join us as we continue to explore the deepest enigmas of our incredible universe.